Complex oxides are attractive materials with ideal properties for making energy-efficient electronic devices and quantum computing devices. However, complex oxide crystals cannot be grown directly on silicon, the most used substrate in microelectronics. Instead, these oxides have to be grown on a compatible substrate, detached, and then carefully transferred to another substrate. Transferred films, however, exhibit different properties than their as-grown counterparts. In their article in Advanced Materials, Dr. Saider Bakal from Argonne National Laboratory and his co-workers conducted experiments to access the dark side, or the interfacial layer, of oxide crystals grown on a substrate. Lead zirconium titanate, or PZT, was grown on a compatible substrate and then etched from it. By carefully flipping the detached thin film and placing it on top of an identical substrate, the bottom side was exposed. Through scanning probe microscopy measurements, the researchers noted that the velocity of domain walls, which gives an idea of the electrostatic energy landscape of the oxide, was 3 orders of magnitude lower on the detached layers compared with the as-grown ones. Such changes in the dynamic properties of the material were later found to be due to the flexoelectric effects that are generated from the nanometric ripples in the transferred film. The flexoelectric effects represent energy barriers for domain walls, thus restricting their movement. Moreover, researchers noted that the static properties of the bottom layer in transferred oxides, such as polarization density, were similar to those of the as-grown films, which is a promising result for future material applications, because this bottom layer will create effective functional interfaces with other materials. Thus, this study paves the way for future microelectronic applications.